Hello, I am Sunita. Welcome to my class. Here I am going to discuss JPSTR science topics according to the syllabus. Here the topic is law of thermodynamics. Let us start the class. Next one, law of thermodynamics. Thermodynamics law define the fundamental physical quantities like energy, temperature, entropy that characterize thermodynamic system at thermal equilibrium. Then thermodynamics law, it will define, otherwise it will tell the fundamental physical quantities like energy, temperature, entropy that characterize thermodynamic system. Otherwise, they will tell the behavior of an thermodynamic system at thermal equilibrium. Then these thermodynamic law represent how these quantities behavior under various circumstances, and also thermodynamics law, it will tells energy, temperature, entropy, how they will behave with different environment, otherwise different circumstances. Then let us study what is meant by thermal equilibrium. Heat will flow till both bodies acquires the same temperature. When two bodies, when they will be in contact with each other, then heat it will flow between the bodies until they acquire same temperature. After they acquire same temperature, then there is no flow of it. At that point, we will consider that two status, otherwise two bodies, they will be in thermal equilibrium. There is no flow of heat take place. Both the bodies, they will acquire same temperature. Heat will flow till both bodies acquire same temperature. This state, when there is no heat flow between the two bodies, when they acquire the same temperature, is known as thermal equilibrium. There are four laws of thermodynamics are given below. First one is zeroth law of thermodynamics, first law of thermodynamics, second law of thermodynamics, third law of thermodynamics. Let us discuss in detail here. Zeroth law of thermodynamics. The zeroth law of thermodynamics states that if two bodies are individually in equilibrium with separate third body, here consider three bodies A, B, C, then this A body is thermally equilibrium with body C, then this B body is thermally equilibrium with body C. Both they will be individually thermally equilibrium with third body C. Then the first two bodies are also in thermal equilibrium with each other. In that case, the first two bodies, individual bodies AB, then after thermal equilibrium with the body, third body C, then finally these two bodies AB, they will be thermal equilibrium with each other. This means that if system A is in thermal equilibrium with system C, system A is thermal equilibrium with system C, and system B is also in thermal equilibrium with system C, then these two bodies like AB are also in thermal equilibrium. This one is nothing but zeroth law of thermodynamics. Consider an example to demonstrate the zeroth law of thermodynamics. Consider two cups AB with boiling water. Consider two cups here AB with boiling water. When a thermometer is placed in cup A, it gets warm up by the water until it reaches 100 degrees Celsius, which is read 100 degrees Celsius. Then here put one thermometer inside a cup A. Then here already you have a boiling water. Therefore, because of the boiling water, inside the thermometer, the mercury, it will reaches the level 100 degree, because 100 degrees Celsius is the boiling point of water. We say that the thermometer is in equilibrium with cup A, then we can tell that the thermometer, it should be in thermal equilibrium with cup A. When we move the thermometer to cup B to read the temperature, it continue to read 100 degrees Celsius. Then take same thermometer and dip in cup B. This cup B also, it contains a boiling water. Then this also, it will show a temperature 100 degrees Celsius. The thermometer is also in equilibrium with cup B. Then we can tell that this thermometer, same thermometer, it will be equilibrium with cup B. By keeping in mind the zeroth law of thermodynamics, we can conclude the cup A, cup B are in thermal equilibrium with each other. Then according to zeroth law of thermodynamics, we can conclude the cup A and cup B, they will be thermal equilibrium with each other, because here thermal equilibrium means Here the temperature of both the cup, it will be 100 degree Celsius, and these two, they will be the thermal equilibrium with a thermometer which is showing a temperature 100 degree Celsius. The zeroth law of thermodynamics enable us to use the thermometer to compare the temperature of any two objects that we like. First law of thermodynamics. First law of thermodynamics, also known as the law of conservation of energy, states that energy can neither be created nor destroyed, but it can change from one form to another form. First law of thermodynamics we can known as the law of conservation of energy. According to this one, energy can neither be created, we can't create the energy, and also we can't destroy the energy also, but you can change the energy from one form to another form. Let us consider an example here. Heat. The flame is created using chemical energy, and the energy from the fire is transferred to the marshmallow through heat energy. Next one, mechanical energy. The gas in the car is burned, generally chemical energy which is converted to mechanical energy. Here you can observe the gas inside the car, when it is start burning, then chemical energy which it will be converted to mechanical energy. When people eat food, chemical energy is converted to mechanical heat and different chemical energies. What we will eat the food, that in that one we are having the chemical energy, that it will be converted into mechanical heat and different chemical energies. The next one, a light bulb is powered by electrical energy which is converted to electromagnetic energy or light. You can see in the bulb having electrical energy, that one we can convert it into electromagnetic energy or light. The first law of thermodynamics may seem abstract, but we will get a clear idea if we look at a few examples of the first law of thermodynamics. First law of thermodynamics, we will feel like it is abstract, but when we studying with an example, then you can understand very clearly. First law of thermodynamic examples: plant convert the radiant energy of sunlight to chemical energy through photosynthesis. Plant, they will prepare the food with the help of the sunlight. Then here they will convert radiant energy of sunlight to chemical energy with the process of photosynthesis. We eat plant and convert the chemical energy into kinetic energy. That plant we will eat, then inside the plant we are having chemical energy, that it will be converted into kinetic energy. For example, we will swim, we will walk, we will breathe. All this one, here the chemical energy, it will be converted to kinetic energy. Then switching on light may seem to produce energy, but it is electrical energy that is converted. When you switch on the light, then may seem to produce energy. Here the electrical energy that is converted. Then here, according to law of thermodynamics, first law of thermodynamics, energy can neither be created nor be destroyed, but you can convert energy from one form to another form. This one we will also call as a law of conservation of energy. Second law of thermodynamics. Second law of thermodynamics states that entropy in an isolated system always increases. Entropy is nothing but a randomness of particles or disorder of a particles. In an isolated system, it will be always increases. What is meant by an isolated system? An isolated system is a special type of closed system that does not even transfer energy across the boundary. Isolated means a closed system, then it will not allow any energy to enter into the system, otherwise it will not leave any energy to out of the system. There is no exchange of energy takes place across the boundary. An isolated system spontaneously evolves towards thermal equilibrium. Thermal equilibrium means throughout the system, the temperature it will be constant, otherwise there is no flow of heat when they will acquire thermal equilibrium. the state of maximum entropy of the system. Then here you can observe a maximum entropy. Maximum entropy is nothing but maximum disorder of the particles, or the otherwise random movement of the particles you can observe in an isolated system. The entropy of the universe only increases and never decreases. Always you have to remember this one. Entropy of the universe, it will be always increases, it will never decreases. Many individuals take this statement lightly and for granted, but it has an extensive impact and consequence. Let us study here. Second law of thermodynamics example. The second law of thermodynamics states that there is a net increase in the entropy. Always in the universe, there will be a net increase in the entropy. Consider putting an ice cube into a cup with water at room temperature. Then here, take a glass of water, then put ice cubes on a water at room temperature. Then the water gives off heat to melt the ice cube. Then the water, it will lose the heat. Then it will gives his heat to ice cube. Then the ice cube, it will start melting. As a result, entropy of the water decreases. The water, it will gives heat to the ice cube, therefore entropy of the water, it will be decreases. At the same time, the ice cubes absorbs the same amount of heat, therefore its entropy increases. The water, it is giving the heat, therefore the entropy of the water decreases. The ice cube, it will absorb the heat, therefore entropy of the ice cube increases. The entropy increases of the ice cube is much greater than the entropy decreases of the water. The entropy, how much entropy it will be increase in the ice cube, it will be more than the entropy decrease in the water. Therefore, there is a net increase in the entropy. Here you can consider, whenever any change in the universe, always there will be a net increase in the entropy. Third law of thermodynamics. The third law of thermodynamics states that entropy of a perfect crystal at a temperature of 0 Kelvin, that entropy, it will be equal to 0. If you consider a perfect crystal at a temperature of 0 Kelvin or absolute temperature, at that particular temperature, entropy of a crystal, it will be equal to 0. Third law of thermodynamics example. Let us consider steam as an example to understand the third law of thermodynamics step by step. The molecules within it move freely, have high entropy. In the case of a steam, you know, all the particles, they will be far from each other. Therefore, the particles, they will possess high kinetic energy. Because of the high kinetic energy of the particles, they will move randomly within the molecule, therefore they will possess high entropy. If you decrease the temperature below 100 degrees Celsius, if you decrease the temperature below 100 degrees Celsius, the steam gets converted to water. Then the steam, it will start converted into a water, where the movement of molecule is restricted, decrease the entropy of the water. Then when the temperature of the steam decreases, then it will start converting into a water. Then the moment of the molecule is restricted. When the moment of molecule is restricted, then automatically the entropy of water, it will be decreases. Entropy is nothing but disorder of the molecule or randomness of the molecule. When water is further cooled below 0 degrees Celsius, it gets converted to solid ice. If you decrease the temperature of the water below 0 degrees Celsius, then it will convert it into a solid ice. In this state, the moment of molecule is further restricted, the entropy of the system is reduced more. When it is converted from liquid to solid, then you know, in the solid harder, all the particles, they will be packed each other, they will be packed perfectly in a regular shape. There is no movement of the molecules, it will takes place. Therefore, entropy of the system, it will still decreases more. As the temperature of the ice further reduced, the movement of the molecules in them are restricted further, the entropy of the substance goes on decreasing. When the ice is cooled to absolute zero, ideally the entropy should be zero. Absolute zero is nothing but you have to make the entropy zero. When the ice, if you cool the ice below absolute zero temperature, at that temperature there is no movement of the particles, it will takes place within the molecule, then the molecule it will possess zero entropy. But in reality it is impossible to cool any substance to zero. Reversible and irreversible process. We see so many changes happening around us every day, such as boiling of water, rusting of iron, melting of ice, burning of water. Here, boiling of water, when you start boiling the water, then it will be converted into steam. If you cool the steam again it will be come back to its original state, that is water. Here you can observe the initial state you can convert into final state. Again if you do some changes, then the final state it will come back to the original state. That one we will call it as a reversible process. Then rusting of iron is an irreversible process because you can't get back to the original state of the iron. Then melting of ice also, this is also reversible process because when you start melting the ice, then it will become liquid. Again if you cool the liquid, again it will be converted into ice. Therefore this is also reversible. Burning of paper, once you burn the paper you can't get back to the original state of the paper. Therefore this is also irreversible process. In all this process we observe that the system is consideration goes from initial state to a final state. Here you can observe the system you can consideration, there will be a change in initial state to final state, where some amount of heat is absorbed from the surrounding, some amount of work is done by the system on the surrounding. All this process, the system it will absorb heat from the surrounding, then that system it will do some work done by the system on the surrounding. Here the system it will receive heat from the surrounding, and also the system it will do some of the work on the surrounding. Now for many of such systems, can the system and the surrounding be brought back to their initial state? That one we will call it as a reversible change. In the case of a reversible change, the system it will receive, otherwise it will absorb some amount of heat from the surrounding, and it will do some amount of work on the surrounding, the work done by the system on the surrounding. Then here the process can be reversible. Reversible means you get back to the original state with common examples such as rusting and fermentation. Here rusting and fermentation, rusting of iron, already I told you can't get back to the iron. Then in the case of a fermentation also, after fermentation you are not get back to the initial state of the matter. We can say that in most of these cases it is not possible. In this section we shall learn about the reversible and irreversible process. Let us discuss in detail what is meant by reversible and irreversible process. Let us consider an example of a reversible process. Here, expansion of a gas. Then here consider this is the piston. At the initially if you decrease the temperature and pressure of a gas, then the gas it will start expanding. When it is expand more, it will reach a maximum expansion, then volume of the gas it will be more. This is the final stage of the piston. This is the initial stage, this is the final stage of the piston. Once it reaches the final stage, then it will start compressing. Then here the temperature and pressure of the gas it is start increasing. When it is reaches maximum temperature and pressure, then you can observe a maximum compression of the gas. Then here you can observe this is the initial process from this one to this one. This is the initial state, then this is the final state, maximum expansion of the gas. Then this is the restoring process. After restoring process, the gas it will be come back to its original state. Then this type of process we will call it as a reversible process. Then here you can observe a maximum expansion of the gas, that is the final state. Again you can observe a maximum contraction compression of the gas. Then here you will get back to the original state, that is nothing but reversible process. What are reversible process? A thermodynamic process state I, it will be give rise to state F, is said to be reversible if the process can be turned back such that both the system and the surrounding return to their original state with no other changes anywhere else in the universe. Here you can observe, according to thermodynamics, reversible process is nothing but every process it will involve a change in the system and the surrounding. There may be a transfer of heat, energy, matter, it will takes place. If these changes come back to its original state, whatever the changes it will happen in system and surrounding, if the changes come back to its original state, then that process we will call it as a reversible process. As we know, in reality, no such process as reversible process can exist, but in the reality, as the existence of reversible process, it will be difficult. Thus, the reversible process can easily be defined as idealization or models of real process on which the limits of the system and device are to be defined. They help us in incurring the maximum efficiency a system can provide in ideal working condition, thus the target design that can be set. Here you have to remember reversible process is nothing but when any changes happened in the system and surrounding, if that changes come back to its original state, that process we will call it as a reversible change. But practically, in the case of a thermodynamic reversible change, it will be minimum. Let us consider few examples of a reversible process. Extension of spring. If you expand the spring, then if you leave the spring, then it will come back to its original state. Slow adiabatic compression and expansion of a gas. In any particular, compression and expansion of a gas is a reversible process. Electrolysis with no resistance in the electrolyte. Electrolysis is also one of the good example of a reversible process. The frictionless motion of a solid, then slow isothermal compression and expansion of a gas. These are the few examples of a reversible process. What are irreversible process? An irreversible process can be defined as a process in which the system and the surrounding do not return to their original condition once the process is initiated. In the case of a irreversible process, whatever the changes it will happen on system and surrounding, then they will not come back to its original state. That one we will call it as a irreversible process. Let us discuss with an example, taking an example of an automobile engine that has traveled a distance with the aid of fuel equal to an amount X. During the process, the fuel burns to provide energy to the engine, converting itself into smoke and heat. Consider, for example, of a car. In the car, you know you are having the engine. Then the engine work. If the fuel burns, then the engine it will start working. Then the car it will cover some distance. Then here the fuel it will burns. Then it will be converted into smoke and heat energy. Energy to the engine, converting itself into smoke. We can't retrieve the energy lost by the fuel and cannot get back the original form. These are the here. Okay. Taking an example of an automobile engine that has traveled a distance with the aid of fuel equal to an amount X. During this process, the fuel burns to provide energy to the engine. If a car wants to move, then the engine it has to need energy. Then the fuel it will burn, then it will give the energy to the engine, converting into smoke and heat energy. We can't return the energy lost by the fuel and cannot get back to the original form. First one, the friction that converts the energy of the fuel to heat energy. The friction it will converts energy of the fuel to heat energy. Second one, the unrestrained expansion of the fluid which prevents from the regaining the original form of the fuel. Heat transfer through a finite temperature. Here heat transformation it will occur at a finite temperature, the reverse of which is not possible as the forward process. In this case, the process is spontaneous. Spontaneous process is nothing but with a limited time, the fuel it will start burning then it will start giving to heat energy. Then reversible process is not possible because the process is spontaneous. Mixing of two different substances which cannot be separated as the process of intermixing is again a spontaneous in nature, the reverse of which is not feasible. Here also mixing of two substances, thus two substance they will mixed with a short interval of time, otherwise spontaneously, then the separation of two substances is impossible. Then here the reaction, otherwise the process, it will take place spontaneously. Thus some processes are reversible while the other are irreversible in nature, depending upon their ability to return to their original state from their final state. Here depending upon the process, some process may be reversible, some process may be irreversible, their ability to come back to their original status from the final state. Some example of irreversible process: relative motion with friction, throttling, heat transfer, diffusion, electricity flow through a resistance. These are the few examples of irreversible process. Thanks for listening my class. Send me your valuable feedback.